Article 518.4b of the National Electrical Code, or NEC, addresses wiring methods in specific occupancies, including churches. Understanding this article is crucial when determining whether Romex, also known as NM cable, can be used in certain areas. Based on the NEC, Romex is permitted in areas that are not fire rated within a church rated as 5A. This allowance directly applies to spaces such as the kitchen, assembly hall, and fellowship hall, provided the building plans confirm that these areas do not require a specific fire rating. However, it is important to differentiate between the NEC minimum requirements and any additional specifications made by an electrical engineer. An engineer might specify that the entire building be wired using metal-clad cable, or MC cable, or conduit, which exceeds the NEC baseline but isn't necessarily a code violation if it enhances safety or meets other design considerations. When facing conflicting instructions, such as the NEC permitting Romex and an engineer requiring MC cable or conduit, it's best to seek clarity from the local building inspector. The building inspector is the final authority on code interpretations and can provide definitive guidance on which requirements must be followed. To ensure compliance and avoid potential rework, firstly, review the building plans thoroughly to confirm which areas are designated as non-fire rated. Secondly, compare these designations with the requirements outlined in NEC Article 518.4b. Thirdly, consult with the electrical engineer to understand the reasoning behind their specifications for MC cable or conduit throughout the building. Fourthly, obtain a formal interpretation from the local building inspector to reconcile any discrepancies between the NEC, the engineer's specifications, and local amendments. In general, the NEC serves as a minimum standard, meaning that an engineer can impose more stringent requirements. However, these requirements must be justified by specific safety or operational concerns. If the engineer's specifications are simply a matter of preference without a clear rationale, the building inspector may allow the use of Romex in non-fire rated areas as permitted by the NEC. It is also crucial to consider any local amendments to the NEC that may be in effect. Local jurisdictions often modify the NEC to address specific regional concerns or to align with local construction practices. These amendments can either restrict or expand the use of Romex in certain applications. Therefore, always check with the local building department to ensure that you are aware of any relevant amendments. When installing Romex cable, adhere to all applicable installation requirements outlined in the NEC, including proper support, protection from physical damage, and appropriate ampacity ratings. Ensure that the cable is not exposed to moisture or corrosive environments, as this can degrade the insulation and create a safety hazard. Also, avoid running Romex cable through thermal insulation unless it is specifically rated for such applications. In summary, while NEC Article 518.4b generally permits the use of Romex cable in non-fire rated areas of a church, it is crucial to consider the engineer's specifications, local amendments, and the interpretation of the local building inspector. Always prioritize safety and compliance with all applicable codes and regulations. Remember that electrical work must always adhere to all applicable codes and standards, as well as any local regulations that may apply. Furthermore, it is always a good idea to consult with a local building inspector to ensure that your work meets their expectations. Understanding ampacity and overcurrent protection is crucial for safe electrical installations. Ampacity refers to the current carrying capacity of a conductor, which is the maximum amount of current, measured in amps, that a conductor can carry continuously without exceeding its temperature rating. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect conductors and equipment from overloads and short circuits. Selecting the correct size and type of overcurrent protection device is essential to prevent fires and other electrical hazards. The NEC provides detailed guidelines on how to determine the ampacity of conductors and how to select appropriate overcurrent protection devices. These guidelines take into account various factors such as the type of conductor, its insulation, the ambient temperature, and the number of conductors a raceway or cable. When determining the ampacity of a conductor, firstly consult NEC Table 310.15b16, which provides ampacity ratings for various types of conductors based on their insulation and temperature rating. Secondly, apply any necessary adjustment or correction factors based on the ambient temperature and the number of conductors in a raceway or cable. Thirdly, ensure that the overcurrent protection device does not exceed the ampacity of the conductor unless specifically permitted by the NEC. Overcurrent protection devices are designed to trip or blow when the current exceeds their rated capacity. Circuit breakers are resettable devices that use a thermal or magnetic mechanism to interrupt the flow of current. Fuses are one-time devices that contain a fusible link that melts and breaks the circuit when the current exceeds their rating. When selecting an overcurrent protection device, firstly, determine the load current that the circuit will be carrying. Secondly, select an overcurrent protection device with a rating that is equal to or slightly larger than the load current, but not exceeding the ampacity of the conductor. Thirdly, consider the type of load that the circuit will be serving, as some loads, such as motors, may require special types of overcurrent protection devices. It is also important to properly install and maintain overcurrent protection devices. Ensure that circuit breakers are properly seated in their panel and that fuses are tightly screwed into their holders. Periodically inspect overcurrent protection devices for signs of damage or corrosion and replace them if necessary. Never bypass or tamper with overcurrent protection devices, as this can create a serious safety hazard. Grounding and bonding are essential for electrical safety. Grounding refers to the intentional connection of a neutral conductor to earth, while bonding refers to the connection of non-current carrying metal parts to create an electrically conductive path. Grounding and bonding help to prevent electrical shock hazards by providing a low impedance path for fault current to flow back to the source. This causes the overcurrent protection device to trip or blow, disconnecting the circuit and preventing a dangerous voltage from appearing on metal parts. The NEC provides detailed guidelines on how to properly ground and bond electrical systems. These guidelines cover various aspects such as the size and type of grounding and bonding conductors, the location of grounding electrodes, and the methods for connecting grounding and bonding conductors to equipment. When grounding an electrical system, firstly, establish a grounding electrode system consisting of one or more grounding electrodes such as ground rods, ground plates, or metal underground water pipes. Secondly, connect the neutral conductor to the grounding electrode system at the service entrance. Thirdly, ensure that the grounding electrode system has a sufficiently low impedance to allow fault current to flow back to the source. When bonding an electrical system, firstly, bond all non-current carrying metal parts, such as equipment enclosures, metal raceways, and metal piping systems. Secondly, use bonding jumpers to connect these metal parts together into the grounding electrode system. Thirdly, ensure that the bonding jumpers are sized appropriately to carry the maximum fault current that may occur. It is also important to properly inspect and maintain grounding and bonding systems. Periodically check grounding and bonding connections for signs of corrosion or looseness, and tighten or replace them as necessary. Never remove or disconnect grounding or bonding conductors, as this can create a serious safety hazard. Electrical panels and distribution boards are the central hubs for distributing electrical power throughout a building. They contain circuit breakers or fuses that protect individual circuits from overload and short circuits. Electrical panels and distribution boards must be properly sized, installed, and maintained to ensure safe and reliable operation. The NEC provides detailed guidelines on how to select and install electrical panels and distribution boards. These guidelines cover various aspects such as the ampacity rating of the panel, the number of circuits that it could accommodate, the location of the panel, and the methods for connecting conductors to the panel. When selecting an electrical panel, firstly, determine the total load that the panel will be serving. Secondly, select a panel with an ampacity rating that is equal to or greater than the total load. Thirdly, ensure that the panel has enough circuit breaker or fuse positions to accommodate all of the circuits that will be connected to it. When installing an electrical panel, firstly, choose a location that is readily accessible and free from obstructions. Secondly, mount the panel securely to a wall or other suitable structure. Thirdly, connect the incoming power conductors to the main lugs of the panel. Fourthly, connect the branch circuit conductors to the circuit breakers or fuses in the panel. It is also important to properly label and maintain electrical panels. Label each circuit breaker or fuse with a description of the circuit that it serves. Periodically inspect the panel for signs of damage or corrosion, and clean it as necessary. Never overload the panel or tamper with the circuit breakers or fuses. Wiring methods refer to the various types of raceways, cables, and conductors that are used to distribute electrical power throughout a building. The NEC specifies the allowable wiring methods for different applications based on factors such as the voltage, current, location, and environment. Common wiring methods include rigid metal conduit, electrical metallic tubing, flexible metal conduit, armored cable, non-metallic sheathed cable, and underground feeder cable. Each wiring method has its own advantages and disadvantages, and the selection of the appropriate wiring method depends on the specific application. When selecting a wiring method, firstly, consider the voltage and current requirements of the circuit. Secondly, consider the location and environment in which the wiring will be installed. Thirdly, consider the mechanical protection requirements of the wiring. Fourthly, consider the cost and ease of installation of the wiring method. Rigid metal conduit provides excellent mechanical protection and is suitable for use in harsh environments. Electrical metallic tubing is a lightweight and cost-effective option for indoor applications. Flexible metal conduit is used to connect equipment that may be subject to movement or vibration. Armored cable, also known as NEC cable, is a self-contained wiring system that provides good mechanical protection. Non-metallic sheathed cable, also known as Romex, is a cost-effective option for residential and light commercial applications. Underground feeder cable is used to run power underground to outbuildings or other structures. It is also important to properly install and support wiring methods. Ensure that raceways and cables are securely fastened to walls, ceilings, or other structures. Use appropriate fittings and connectors to make electrical connections. Avoid running wiring through areas where it may be subject to physical damage or moisture. Lighting is an essential aspect of electrical design, providing illumination for various tasks and activities. The NEC provides guidelines on how to properly design and install lighting systems, based on factors such as the type of occupancy, the level of illumination required, and the energy efficiency of the lighting fixtures. When designing a lighting system, firstly determine the illumination levels required for the various tasks and activities that will be performed in the space. Secondly, select lighting fixtures that are appropriate for the application and that meet the energy efficiency requirements of the local building code. Thirdly, consider the color rendering properties of the lighting fixtures, as this can affect the appearance of objects and the perception of colors. Fourthly, consider the control options for the lighting system, such as dimmers and occupancy sensors. There are various types of lighting fixtures available, including incandescent, fluorescent, light-emitting diode, and high-intensity discharge fixtures. Incandescent fixtures are the least energy efficient but provide a warm and pleasing light. Fluorescent fixtures are more energy efficient than incandescent fixtures and provide a more diffuse light. Light-emitting diode fixtures are the most energy efficient and have a long lifespan. High-intensity discharge fixtures are used for high bay lighting applications. It is also important to properly install and maintain lighting fixtures. Ensure that fixtures are securely mounted and that electrical connections are properly made. Clean fixtures regularly to maintain their light output. Replace lamps or bulbs as needed to ensure that the lighting system continues to provide adequate illumination. Motors are widely used in electrical systems to power various types of equipment such as pumps, fans, compressors, and machinery. The NEC provides detailed guidelines on how to properly size, protect, and control motors. These guidelines cover various aspects such as the motor's full load current, the motor's starting current, the motor's overcurrent protection requirements, and the motor's control circuit requirement. When sizing a motor, firstly determine the load requirements of the equipment that the motor will be driving. Secondly, select a motor with a horsepower rating that is equal to or greater than the load requirements. Thirdly, consider the motor's speed and torque characteristics, as these can affect the performance of the equipment. When protecting a motor, firstly, provide overcurrent protection to protect the motor from overloads and short circuits. Secondly, provide thermal overload protection to protect the motor from overheating. Thirdly, provide ground fault protection to protect the motor from ground faults. When controlling a motor, firstly, provide a means of starting and stopping the motor. Secondly, provide a means of controlling the motor's speed. Thirdly, provide a means of protecting the motor from undervoltage conditions. There are various types of motor controllers available, including manual starters, magnetic starters, and variable frequency drives. Manual starters are simple and inexpensive but offer limited protection. Magnetic starters provide better protection and can be remotely controlled. Variable frequency drives provide precise speed control and can improve energy efficiency. It is also important to properly install and maintain motors and motor controllers. Ensure that motors are properly aligned and lubricated. Inspect motor controllers regularly for signs of damage or wear. Replace motor controllers as needed to ensure reliable operation. Transformers are used in electrical systems to step up or step down voltage levels. They consist of 2 or more coils of wire wound around a common core. The ratio of the number of turns in the primary coil to the number of turns in the secondary coil determines the voltage transformation ratio. The NEC provides guidelines on how to properly size, protect, and install transformers. These guidelines cover various aspects, such as the transformer's kilovolt amps rating, the transformer's overcurrent protection requirements, and the transformer's grounding requirements. When sizing a transformer, firstly, determine the load requirements of the equipment that the transformer will be serving. Secondly, select a transformer with a kilovolt amps rating that is equal to or greater than the load requirement. Thirdly, consider the transformer's voltage transformation ratio, as this will determine the output voltage. When protecting a transformer, firstly, provide overcurrent protection on the primary side of the transformer to protect it from overloads and short circuits. Secondly, provide overcurrent protection on the secondary side of the transformer to protect the downstream circuits and equipment. Thirdly, provide ground fault protection to protect the transformer from ground faults. When grounding a transformer, firstly, ground the transformer's enclosure. Secondly, ground the transformer's secondary winding if it is a Y-connected system. Thirdly, ground the transformer's neutral point if it is a delta-connected system with a center tap neutral. It is also important to properly install and maintain transformers. Ensure that transformers are properly ventilated to prevent overheating. Inspect transformers regularly for signs of damage or leaks. Test transformer oil periodically to ensure that it is free from contaminant. Renewable energy sources such as solar photovoltaic systems and wind turbines are becoming increasingly popular as a way to generate electricity. The NEC provides guidelines on how to properly install and connect renewable energy systems to the electrical grid. These guidelines cover various aspects, such as the system's voltage, current, and power ratings, the system's grounding requirements, and the system's disconnection requirements. When installing a solar photovoltaic system, firstly, determine the size and orientation of the solar array. Secondly, select solar panels and inverters that are appropriate for the application. Thirdly, install the solar array securely to a roof or other suitable structure. Fourthly, connect the solar array to the electrical grid through a suitable disconnect switch and overcurrent protection device. When installing a wind turbine, firstly, determine the location and height of the wind turbine. Secondly, select a wind turbine that is appropriate for the application. Thirdly, install the wind turbine securely to a tower or other suitable structure. Fourthly, connect the wind turbine to the electrical grid through a suitable disconnect switch and overcurrent protection device. It is also important to properly maintain renewable energy systems. Inspect solar panels and wind turbines regularly for signs of damage or wear. Clean solar panels is needed to maintain their efficiency. Test batteries periodically to ensure that they are functioning properly. Understanding and applying these electrical concepts is essential for safe and reliable electrical installations. Always consult with a qualified electrician or electrical engineer if you have any questions or concerns.